Okay, so welcome back to another video. So we have a crazy limit we're actually dealing with consisting of factorials. So what we have is the limit as x approaches 0 of the x factorial minus 1 root of x plus 2 factorial quantity divided by 2 quantity factorial, all this being divided by x minus 1 factorial times sine of x. So factorials, we got this one trigonometric function included into our limit. So how do you think we're going to approach something like this? Well, we're just going to rely on just this one easy trick. Turn all the factorials in terms of the gamma function, since that is by the definition. So with that in mind, that'll make things a little bit easier in terms of simplification, and it'll actually cancel some stuff down. And as we continue forward from this, overwhelming limit we're actually dealing with, that we actually got a bunch of special functions. We'll be using it in an interesting summation series that's going to be utilized as well. And with all that, it's actually just going to come down to a nice answer. Well, the answer as the final value of the answer is going to consist of a bunch of things, but at least it actually reduces to something / converges to the value. So that in mind, let's actually just jump right in. So of course, as mentioned, we're going to turn everything in terms of the gamma function. So let's actually reiterate and say that gamma of x is simply just going to equal to x minus 1 quantity factorial. And that is, of course, for x is actually a positive integer. So with this, I'm going to call this capital L. And now let's actually convert everything back in terms of the gamma function, replacing with the factorials. So what we have now is that the limit as x approaches infinity. So we replace x factorial, so that'll give us gamma of x plus 1, then subtract 1. So that's, of course, just under that root, the radical. Then we can actually simplify this here. So quantity factorial, and then inside that factorial quantity, we have another factorial. So that'll lead us with, if we put in the right inputs, we have gamma of x plus 3, then divided by 2, then add this with 1, okay, and that just encloses that out. So now under the denominator, what we have now is x minus 1 factorial, and then sine of x. Here's a little thing I'm going to do that's very interesting. So what I'm going to do is I'm actually going to multiply and divide an x. So the x is being multiplied with the x minus 1 factorial. So x minus 1, then factorial, all this being divided by, so sine of x, and then, well, we're dividing the x into the sine function over here. Okay, so now we can actually simplify some things further. So now I have now the limit, x approaches 0. So what we have now is that, of course, I'm actually going to write this radical in terms of the exponent. So that means the exponent is going to be a fraction, a rational function rather. So now that'll yield us with the following. So now we'll get just gamma of x plus 3 divided by 2. Add this with 1, close this off, and then what we have is that exponent is to the power of 1 divided by gamma of x plus 1 and then minus 1, okay? And then under the denominator, as I mentioned, so we multiply divide x, but actually reduces x times x minus 1 factorial is simply just the same thing as x factorial, but we'll put that back in terms of the gamma function, which x factorial is simply just going to equal to gamma of x plus 1, and then we just have sine of x divided by x. Okay, so now here's some things that we want to identify. Let me actually just box this so far of what we have achieved for. So here's some things we want to identify. So we note that specifically, if I were to take this in terms of the limit from the continuity, that the limit as x approaches 0 of gamma of x plus 1, well, if I were to take that limit, I just have gamma of 1, which gamma of 1 is simply just going to be just 0 factorial, which of course that just evaluates to simply just 1. And then we have another limit, the limit as x approaches infinity of sine of x divided by x. We all know that this is actually just simply just going to equal 1. You see this formula a whole lot when you're in the introductory calculus course. So that's great because that means that this denominator is actually just going to completely vanish. And what we have now is that L is simply just going to be just the following numerator. So x approaches 0, and then we just have gamma of x plus 3 divided by 2. Add this with 1, and then now just take that exponent, so to the power 1 divided by gamma of x plus 1, and then subtract 1. Okay, So now that actually simply reduces some stuff down. So why don't we actually take things one step further, and in order to continue performing this limit, let's actually use the nice trick with e to the ln, because if you take that, that means you just get this. So we're actually rewriting this in another simple way. So now L is going to be now just equal to e, and in terms of continuity, we can actually just take the limit of that exponent. So now it's just going to be e and n to the power. So now write this, let me put this in the parentheses, x approaches infinity, or x approaches 0, excuse me, of just now, we have now the ln, the natural log. So the natural log of gamma x plus 3, and then divided by 2, and then add this with 1, close this off, and then now this is simply just going to be divided by gamma of x plus 1, and then subtract 1. Okay, so closes that off. And so now we just have this limit we have to deal with. So let me actually put an asterisk just to show that we're now just paying attention to our exponent over here of the e base. So as you notice that we actually applied the limit as it approaches 0. So that means over here we actually get a 0, since gamma of 0 plus 1 is gamma 1. So 1 minus 1, 0. Over here, gamma of 3, which is going to be 2 factorial, so 2 divided by 2, 1, then plus 1, so gamma of 2, which is the same thing as 1 factorial, which is 1, then ln of 1, 0. So 0 over 0, we get something of an indeterminate form, then we can actually apply L'Hopital's rule. So of course, over here with the natural log, so we apply yet the natural log derivative of that, the logarithmic derivative. So take the derivative of the numerator and the denominator. So what we have now is actually going to be the limit as x approaches 0. So first, we're just going to leave this as the differential, so the derivative d over dx of what's inside the input. So gamma of gamma x plus 3, and then divided by 2, add this with 1, so close this off. Then under the denominator of that is actually just applying, just taking whatever that input is, so gamma of x plus 3, then divided by 2, add this with 1. So under that denominator is that we're actually taking the derivative of this, which we're just going to leave that as gamma prime of x plus 1, and minus 1, of course, derivative is just 0, so we're just going to leave that the way it is. So let's actually fix this. It's simplifying some things out that we're not really simplifying, just so we have everything just in one fraction and not dealing with two different divisions over here. So now we just simply need to have d over dx of gamma of x plus 3 divided by 2 plus 1. So close this off, and then now divided by, so simply just gamma and then gamma of x plus 3. Let me fix that for 1 second. All this being divided by 2 plus 1, and then multiply with gamma prime of x plus 1. Okay, so that's what we're dealing with so far. So now we can actually now apply this even further, taking the derivative of this input, such that this is actually yet again just applying chain rule, meaning that I just take the derivative, so this is gamma prime of this, and then multiply with whatever is the derivative of the inside. So now L, or not yet, just continue on with this limit over here. L is not what we're dealing with just yet. So limit as x approaches 0. So what we have is gamma prime of gamma x plus 3 divided by 2 plus 1, and then take the derivative of the inside, which is actually just going to be gamma prime of x plus 3 divided by 2, and then under the denominator, nothing has changed. And now if I were to take this limit, so now let me draw this arrow to say that now we have that L now so far is going to be E. Now we take this entire limit over here. So this is going to be a big one. So plug in 0. So gamma of 3 divided by 2, then plus 1. And then afterwards plug into 0. So that means gamma prime of 3 divided by 2. So let me actually write this out in full before I forget. So gamma prime of gamma 3, then divided by 2 plus 1. Okay. And then now multiply with gamma prime of 3, then divided by 2. Under that denominator, now we just plug in that limit. So that means now we have gamma prime of 1, and then multiply with gamma of 3, then divided by 2, and then plus 1. Okay, so this is what we're dealing with so far. So I know it looks like a lot, but now we're actually going to use a couple functions that are actually going to make the evaluation more simple. So notice that by definition, what we're actually going to be using is we're actually going to be using the digamma function, which of course is the natural, I keep saying natural, the logarithmic derivative of the gamma function. So that means, let me write the note here. So dx of ln of gamma x is simply just going to equal to gamma prime of x divided by gamma x. Okay, And then another thing we'll be using, so let me actually write this. So the notation is going to be psi of x as a digamma function. Another piece of critical information we'll be using is that gamma of n has that nice identity. So it's going to be equal to h sub n minus 1, this being the n minus 1 harmonic number, then minus lowercase gamma, aka the Euler-Mascherodi constant. And so with this, now we can actually now simplify some things over here that we can now reduce to. So now so far, if I reduce everything down from right here, what we're going to have now so far is that this is going to be e, and then now to the power, so gamma prime of 2, since since thing from earlier, so gamma of 3, that's going to be 2 factorials, so 2 divided by 2, then 1, so 1 plus 1 is 2. Okay, and then we just apply the same thing over here of gamma prime of 3. So we can't do anything with that just yet, so we're just gonna we're gonna leave that the way it is for now before we continue further. So all this being divided by, so gamma of 2 and then times gamma prime of 1. Let me move the e down just a little bit. Now we can further reduce, of course, gamma of 2, which is actually just going to equal 1. And then I have that the 1/2 over here, so let me move that outside. So this is going to be e to the power 1/2. Then times, so that means we have just gamma prime of 3 multiplied by gamma prime of 2, all this being divided by gamma prime of 1. And then we can actually use a nice trick in order to utilize the digamma function, of course from over here from this, that we have primes and then we have the gamma function. We can reduce to say that this is the identity of just e to the power 1/2 multiplied by gamma of 3 multiplied by the digamma of 3, multiplied with gamma of 2, multiplied the digamma of 2, all this being divided by gamma of 1 multiplied by the digamma function of 1. Okay, so here's some numbers that I'm actually gonna put into the simplification over here. So of course we have digamma 1, 2, and 3, so let's actually put that back in. So let me put a note, digamma of 1, so utilizing that definition, so h sub n minus 1, that means that's just the zero harmonic number, aka just equal to 0, so we have negative lowercase gamma. Digamma of 2, which I put this in, so the harmonic number is going to be, so 2 minus 1, so the first harmonic number, which is just going to equal just 1, and then minus lowercase gamma, and then digamma of 3, so that means I have the second harmonic number, so 1 plus 1/2, so that's 3 over 2, and then subtract the lowercase gamma. Okay, so now with that in mind, now let's actually plug in the pieces back together. So over here, so I'm gonna put L, then e to the power 1/2, and then multiply by, so now gamma of 3, of course, is actually just 2 factorials, that's 2. Gamma of 2 is actually just equal to 1, and then gamma of 1 is actually just gonna equal 1. So now put everything back together, so I have 2, and then substitute the digamma of 3, so 3 over 2 minus lowercase gamma, and then multiply with 1 minus lowercase gamma from the digamma of 2, all this being divided by, so gamma of 1, as I said, is 1, then digamma of 1 is actually just negative lowercase gamma. If I substitute it, or not substitute, if I simplify this all out, I have now e to the power, so lowercase gamma, hold on, I gotta reduce the size of that, lowercase gamma minus 1 multiply with 3 minus 2 times lowercase gamma, all being divided by 2 times lowercase gamma. And if you want to reduce this even further, and this is actually exactly what Wolfram Alpha has to put in the result, this actually just equals to e to the power 5 divided by 2 minus lowercase gamma, and then minus 3 divided by 2 times lowercase gamma, which indeed is the final answer to this crazy limit of factorials. And of course, as mentioned, it actually does converge to some value, as we notice right here. So a crazy limit, a very interesting one indeed, with all this messy work that you just see everything in terms of everything with a lot of gammas, and then we reduce with the definition of the digamma function and utilizing the harmonic number as well. So there you have it. So yeah, that's pretty cool if you ask me.